Imagine you've gone off-roading and your Jeep gets stuck deep in the mud. You have a massive, heavy machine completely trapped in place. To get it out, you have two basic options. You can pull it forward using a winch on the front bumper, or you can have a friend push you from behind with their truck. Both methods apply concentrated physical force to move the vehicle forward. Many people intuitively divide the physical world into objects that are sitting completely still and objects that are actively moving. But a car parked in a driveway and a spacecraft coasting through a vacuum at a constant 10,000 miles per hour, they share the exact same mechanical state. From an engineering perspective, the division of mechanics is determined by whether a system's movement is accelerating. To calculate that acceleration, engineers use vectors. A vector provides a specific magnitude and a direction of application. It describes how much force is pushing and exactly where it is pointing. These vector forces are governed by Newton's second law of motion. Force equals mass times acceleration. The left side calculates the sum of all forces pushing on an object, and the right side calculates the resulting motion. When an object is at rest or moving with constant velocity, the acceleration is zero. Multiplying mass by zero forces the entire right side of the equation to zero. This creates a state of equilibrium. Forces like gravity, tension, and friction are all present, but they perfectly counteract each other, so the net force remains at zero. This zero acceleration condition is the basis of statics. This educational flowchart shows how statics serves as the prerequisite for analyzing structures where motion is restricted and forces are held in balance. Statics focuses on the analysis of these stable systems, ensuring that opposing internal and external forces remain in a permanent state of equilibrium. When a new, unbalanced force is introduced to a stable system, that equilibrium is lost. Because the object is now accelerating, the right side of Newton's equation becomes a factor. The sum of the forces no longer equals zero, moving the analysis into the branch of dynamics. Dynamics is divided into two sub-branches. The first is kinematics, which maps the geometry of motion. It tracks displacement, velocity, and time, without considering the physical forces that cause the movement. Engineers use calculus to bridge these values. Through differentiation, displacement is converted into velocity, and velocity is converted into acceleration. The second sub-branch is kinetics. This focuses on the relationship between the applied external forces and the resulting change in the object's momentum. Dynamics provides the framework for understanding how unbalanced forces and time modify the state of a physical system. Civil engineering relies on statics to keep structures like skyscrapers and dams in a stationary form. These designs must account for immense loads, such as gravity and water pressure, and lock them in place. To maintain the stability of these massive structures, the sum of every force acting on the system must constantly equal zero. Mechanical and aerospace engineering often prioritize the opposite. Machines are designed to manipulate momentum and manage the dynamic loads that occur as parts move through space. For these systems to function, engineers use the mass and acceleration components of Newton's equation to dictate how the machine responds to force. Every physical object exists within a continuous interaction of vector forces. The mathematical distinction between statics and dynamics allows engineers to solve for two different goals, either securing forces in perfect equilibrium or harnessing those forces to create controlled, predictable motion.